You know, there's something you use every single day, multiple times a day actually, that you probably never really think about. Your tooth enamel. And it turns out its story is less about dental hygiene and more like a superhero origin story than you could ever imagine.
So let's just dive right in. Your tooth enamel is, without a doubt, one of nature's most incredible creations. It's way more than just a hard coating on your teeth. It's what you'd call a genuine supermaterial.
Okay, quick pop quiz for you. If you had to take a guess, what would you say is the absolute hardest, toughest substance in your entire body?
If your brain immediately went to bones, hey, that's what most people would say, but it's not right. The real answer is your tooth enamel. It is this ridiculously mineralized, super dense protective shield that's literally built to last a lifetime of crushing, grinding, and chewing.
But here's the catch. The one fatal flaw in this otherwise perfect design. Once enamel is gone, whether from a cavity or just wear and tear, it is gone for good. Our bodies just can't make more of it. And that, right there, is the fundamental challenge behind almost all of modern dentistry.
So if our bodies can build this stuff once, who or what is doing the building? Well, let's meet the architects of this incredible material.
The undisputed hero of this story is a tiny cell called the ameloblast. Think of it like a highly specialized, single-purpose biological factory. Its one and only mission in life is to produce and perfectly arrange all the building blocks of tooth enamel.
And these cells, they have a very distinct life cycle. A whole career path, really. First, in the pre-secretory stage, they basically tool up and get ready for the big job. Then comes the secretory stage, where they're actively churning out the enamel matrix. And finally, they shift gears to a post-secretory stage, where they help the new enamel harden and mature, before they completely disappear.
Okay, so we've met the construction crew, but what's their blueprint? How does this process of building enamel actually work?
The whole process is called amelogenesis, and you can break it down into three main stages. First, the ameloblasts lay down a kind of soft protein scaffolding. Then, in the mineralization stage, that scaffold starts to get flooded with calcium and phosphate ions, and it begins to harden. And finally, during maturation, it all cures into that final, ultra-hard crystalline structure we know as enamel.
And the final product of all that hard work? It isn't just a shell. It's an incredibly complex, intricately engineered crystalline fortress.
You see, the real secret to enamel's unbelievable strength is in its microarchitecture. If you could zoom in, way in, you'd see it's made of millions and millions of tiny building blocks called enamel prisms, or sometimes enamel rods.
Now, these rods aren't just stacked like bricks. They have this really cool keyhole shape, and they're woven together in this complex, beautiful pattern that runs perpendicular to the tooth's surface. This structure is pure genius. It's what allows the enamel to dissipate incredible forces every time you chew, preventing it from just shattering.
And the density of these things? It's just mind-boggling. A single upper molar can have as many as 12 million of these individual enamel prisms all packed together. That's more than the entire population of New York City in one tooth.
So you might be thinking, okay, microscopic rods, why do I care? Well, your dentist cares. A lot. This quote explains why. Essentially, when a dentist puts in a filling or a veneer, the adhesive, the glue, sticks best to the ends of these rods. So if the tooth surface isn't prepared just right and those rod ends aren't exposed properly, the bond will be weak and the restoration is pretty much guaranteed to fail. It's microscopic engineering with huge, real-world consequences.
But this whole delicate construction process depends on a flawless genetic blueprint. So what happens if there's a typo in the code?
Well, that leads us to a group of genetic disorders known as amelogenesis imperfecta, or AI. For people with AI, the instructions for the ameloblasts are faulty from birth. The enamel just doesn't form correctly, and it leads to teeth that are weak, often discolored, and incredibly prone to breaking down.
Now, it's considered a rare condition, but it affects roughly 1 in every 14,000 people. To put that in perspective, in a city the size of San Francisco, you'd likely find more than 60 people living with this condition.
And as you can see, the visual impact of the condition can be really profound, creating a lifetime of dental challenges and affecting a person's quality of life.
The condition isn't just one single thing. It's generally broken down by the type of defect. In what's called the hypoplastic form, the problem is quantity. There just isn't enough enamel, so it's very thin. But in the hypomineralized and hypomature forms, the problem is quality. The enamel might be the normal thickness, but it's soft, chalky, and just chips away easily.
And all of this brings us to our final chapter, the holy grail of dental science, the quest to figure out how to rebuild enamel.
Right now, scientists are attacking this problem from every angle you can imagine. Some are trying to mimic nature, literally growing synthetic enamel in a lab. Others are using these amazing little molecules called peptides that can build themselves into a scaffold, encouraging new minerals to form right on the tooth. And then, of course, there's the big one, cell-based strategies, looking at stem cells to see if we can maybe grow brand new amyloblasts from scratch.
But the biggest hurdle, the one that brings our entire story full circle, is this. Remember those master builders, the amyloblasts? They complete their job and then they are gone, lost forever once the tooth pushes through the gums. We can't just switch them back on because they're not there anymore.
And so we're left with this massive, tantalizing question for the future. With everything we're learning, could we one day crack this problem? Could we actually harness these technologies to regrow our own enamel? The answer, whatever it is, could completely change medicine and improve millions and millions of lives.